Hello, students. So, it's entirely possible that Friday of this week I will be here and we will have class. However, there's also the real possibility that I won't be here, and so we will not have class. In that case, I'd like to record this lecture, which many of you will find mostly a review. Hopefully there will be some things that will be new. So it's all about complex numbers. Let's motivate them from the language of solving degree 2 polynomial equations. So let's use what we know. Let's try to solve that polynomial equation, x squared plus 2x plus 2. I'll be back in a moment. All right, so let's try to solve this polynomial equation. And you may well already have done using, say, the quadratic formula, which is fine. Just for emphasis, maybe I'll use completing the square to do it. So I will rewrite that via the completing the square formula as x plus 1 quantity squared minus 1 plus 2. So that's x plus 1 squared plus 1. We want to set that equal to 0. So we get x plus 1 squared equals negative 1. And we immediately see something bad. So x plus 1 should be plus or minus the square root of negative 1. Which is, of course, not a real number. Excuse me. So we see immediately there are no real solutions. But what if we just pretend that the square root of negative 1 is a thing? Let's just pretend there is a square root to negative 1. Then we can continue solving and eventually get x equal to negative 1 plus or minus the square root of negative 1. So in that sense, this solves x squared plus 2x plus 2 equals 0. In that sense, this equation does have a solution. It's just not a classical number. We produced a solution. And let's try to motivate why that's an okay thing to do. So let's talk about the development of even what numbers are. So let's suppose you're only allowed to look at counting numbers, 0, 1, 2, 3, 4. Maybe they seem like perfectly reasonable numbers to use, right? Those are the numbers that you see if you're counting things. How many pigs do you have in this pig pen? 0 of them. But if you're only allowed to look in there, does this equation have a solution? So let's suppose that I want to add 2 pigs to this pig pen and wind up with 1 pig in the pig pen. You see that, no, it doesn't have a solution. Instead, that solution is an integer. That's counting numbers and then also negative counting numbers. So if you're only allowed to look at integers, then maybe that's enough. Maybe everything you would want to solve is suddenly solvable. Well, of course it's not. 2x equal to 1, does that have a solution? No. If you like, its solution is a number which when you multiply by 2 gives you 1. But things multiplied by 2 are even numbers and 1 is odd. So there is no solution there. But it does have a solution. Its solution is a rational number. Okay, so there are lots of rational numbers. We now have lots of things to work with. Well, if you're allowed to only look at rational numbers, does x squared equal to 2 have a solution? It turns out the answer is no. It takes a little bit of jiggery-pokery to convince yourself of that. Instead, that number, the square root of 2, is what's called a real number. So you have to keep on inventing these new and broader classes of numbers, and eventually you walk away to an equation like x squared equal to negative 1, or x squared plus 2x plus 2 equals 0. And these don't have solutions. Does this have a solution? No. So instead, the solution to this equation is something else. It's what we'll call a complex number. So let's take a while and just explore what are complex numbers, what do you do with them, what is the algebra of complex numbers, right? If it's reasonable to call them numbers, you better be able to add, subtract, multiply, and divide them. So first, let's describe all the complex numbers. So there, if you like, they're what you get when you create a new imaginary unit, which we'll call I, which has the property that I squared equals -1. And I is often called the square root of -1, and we'll even write I equals square root -1. But this is the main thing to remember about complex arithmetic. You have this new number I whose square is -1. A complex number is anything that can be written as a real number, A, plus B, another real number, times I. So if you like, this portion is purely imaginary. In that part, like, it has this entirely imagined new unit. Well, so let's see. If b is equal to 0, then a plus bi, well, that's just a. Then it's just a real number. If a is equal to 0, if the real part is equal to 0, then a plus bi is just bi, is what's called imaginary. And maybe I'll even specify this. That number a is the real part of a plus bi. bi is the imaginary part. Cool. So so that's what the complex numbers are. Let's think about some things that you can do with them. So you can add numbers together, so you better be able to add complex numbers together. And addition is super easy. Just gather together all the parts that have i's in common. So a plus bi, complex number, plus c plus di plus a complex number is add the real parts together, add the complex parts together. So addition is super easy. Oh, Chris. Hopefully you saw what I meant to write instead of what I actually wrote. To subtract, do the same thing, but subtract. To multiply, all you've got to do is FOIL, and remember that I squared is -1. So let's just FOIL this out and see what happens. We'll get a formula at the end, but the formula isn't the thing that I want you to remember. The process is. So to multiply things together, well, let's FOIL out. First, a times c, there's a real number, plus outside, a di plus inside, oops, I missed, bci plus bi times di. So I guess that's bd times I. But remember, the one thing you need to remember if you want to do complex arithmetic is I squared is -1. And if you remember that, then, well, sorry, I've got some sinusy stuff going on, ear pressure. Okay, so let's just combine some terms. So I see AC minus BD. Plus, well, this one's multiplied by I, that's multiplied by I, let's just factor out that I. AD plus BC I. Nice, so let's just see this in practice. Let's add and subtract and multiply some things. So let's start by, I don't know, doing some addition and subtraction. So remember, you just do this term-wise. So I see 4 minus 2 in the real part, plus 3 minus 2i, so 3 plus 2i, plus 7, all that multiplied by I, which, of course, goodness, simplifies down to, I guess, just 2 plus 5, 12i. Let's multiply some things together. 4 plus 3i times 2 minus 2i. First, 4 times 2 is 8. Outside, 4 times minus 2 is minus 8. I. Inside, plus 6i. And last, 3 times 2 is 6, so minus 6i squared. But remember, that I squared is minus 1. So this minus 6i squared is really plus 6. So the result is 8 plus 6, also known as 12, I guess? No, 14. Arithmetic is hard. Minus 2i, because 8i minus 8i plus 6i leaves you with minus 2i. Seem okay? Good. So let's talk about 1 plus I to the power 4. Just to do another computation. And the answer will actually be kind of a cool answer. So let's think about what 1 plus I to the 4th is. So I guess that's 1 plus I times 1 plus I times 1 plus I times 1 plus I. And so if we can just do these multiplications, we'll be done. So let's just work out what 1 plus I times 1 plus I is, and then we'll know what 1 plus I times 1 plus I is, and we just need to multiply those two numbers together. So doing that, 1 plus I minus 1. If you like, this one is the one that comes from the I squared. And it's multiplied by itself, 1 plus I minus 1, and of course this simplifies to 2i times 2i, right? There's some cancellation, 1 minus 1, 1 minus 1, which is of course 4i squared. Hey, but that's just negative 4. So that's neat. This has just generated a number whose 4th power is negative 4. Negative 4 has a 4th root in the complex numbers. And in fact, there's a general philosophy at play here, which we won't prove in any sense. Polynomials always have solutions if you look in the complex numbers. Every polynomial can be solved. All right, so for any complex number a plus bi, so my next goal is to do division. I want to be able to figure out how to divide things. And in order to divide things, I'll need to build up the idea of the complex conjugate, which I'll do right now. For any complex number a plus bi, its complex conjugate is given by a plus bi bar a plus bi bar equal to a minus bi. So what is this? So if you draw a line atop a complex number, you mean conjugate. And that's what this line is. So let's do some examples. Let's multiply together some numbers. 4 plus 3i times 4 plus 3i complex conjugate. So that'll be 4 plus 3i. And this example is actually important, in that we'll see something really interesting as a consequence. So that's 4 plus 3i times 4 minus 3i. Now let's FOIL it out. 4 times 4 is 16. 4 times minus 3i is minus 12i, plus 3i times 4 is 12i. 3 times 3 is minus, 3 times negative 3, so it's minus 9, and then there's an I squared, so there's an extra 9, equals just 16 plus 9. also known as 25. So there's a cool fact that is apparent from this. A plus bi times the conjugate of a plus bi is always real, and in fact, we can even write down what real number it is. I'll pause for a second, walk this out yourself, and then hit play again, and then we'll talk through it. Okay, good. Everyone did that. Let's do it. So a plus bi times a plus bi bar, that's a plus bi times a minus bi. And now let's just FOIL out. I'm going to switch colors just because I think I'm going to run low on space. So that's a squared minus abi plus abi. And then the final term, b times minus b, so minus b squared times I squared plus b squared. It's always a squared plus b squared. So a plus bi times the conjugate of a plus bi is always a squared plus b squared. And here's the payoff. That is always a real number. Okay, so that's like a reason to care about complex conjugates. You can use it to multiply and turn something into a real number. But, I don't know, maybe you're not impressed by that. That's fair. Let's see what happens. Let's see how we can use that to divide. So let's divide, and here's how we'll do it. We'll start by multiplying and dividing by the complex conjugate of the denominator. Because the problem is I don't know how to divide by a complex number. So let's multiply everything by the thing that I need to multiply by in order to turn the denominator into a real number. 1 plus I divided by 3 minus 2i. That's the same as 1 plus I divided by 3 minus 2i. But then I'm going to multiply the numerator and the denominator by 3 minus 2i. The conjugate of 3 minus 2i, which is, of course, 3 plus 2i. Let's expand this out. I'm going to maybe not quite follow the script because I'm going to get spacing issues if I do. So I already know what's going to be in the denominator. The denominator will be a squared plus b squared. It'll be 3 squared plus 2 squared. And so I know that's what it'll be without actually doing anything. You can FOIL it out and see what happens on your own, but I'm not going to. I know that this is always a squared plus b squared. Let's look at the numerator now. So I'll see 1 times 3. That is 3 plus 2i plus 3i, 3 plus 5i, I times 2i minus 2. So I guess expanding out, simplifying, I see 3 minus 2 divided by 13. That's 1/13th. Then 5i divided by 13i. That's 5/13ths I. So gathering together these like terms, we see that this quotient is actually 1/13th plus 5/13ths times I. So here's the payoff. You can always divide. If you divide a complex number by another complex number, there are the instructions for how to do it. Cool. And I think that I'm not going to do this next one. I'm going to say if you want more practice, you should do it. And then I'll even say once you're done doing that, check using Wolfram Alpha. Have Wolfram Alpha compute this, or any other computer tool you want. I don't actually care. Walk that out, see if you get a correct answer doing this. Nice. So, complex numbers and algebra done. You now know how to do algebra with complex numbers. But why should you care about complex numbers? Well, complex numbers, fairly obviously, are exactly where quadratic equations have solutions. And in fact, quadratic equations have solutions because of the quadratic formula. So does every other polynomial equation, but that's a little bit harder. So the point is that you can take square roots, even of negative things. Square root of negative 5 is, well, square root of negative 1 times 5 is the square root of negative 1 times negative 5. That's just I root 5. Similarly, the square root of negative 100 is I times the square root of 100. There's I times 10, or 10I, whichever way you want to write that. And so part of the point is you can use the quadratic formula even in this setting. You can take square roots. And the quadratic formula just has a square root, so you should be able to walk it out just fine. X squared plus 2x plus 2. Let's walk out the solutions to that. I guess we already know what they will be by completing the square, but let's use the quadratic formula for now, just to do it. So we wind up with x equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And now we simplify it out, we see what happens. See, negative 2 plus or minus the square root of, so I guess that's 4 minus 8. 4 minus 8 is negative 4, all over 2. Simplifying a little bit more, I see negative 2 plus or minus I times, let's see, that's, the I accounts for the negative sign under there, then the square root of 4, which is 2, over 2. But the 2's will cancel, right? That's the same as negative 1 plus or minus I. Which, I don't know, it's compelling that, hey, look, we got the same answer when we used completing the square, which is a less high-tech strategy. The point is the quadratic formula still walks. The quadratic formula still says that ax squared plus bx plus c has solutions equal to x equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's take a look at one particular bit of this formula, the stuff under the square root. So let's think about that. So this quantity, let's see, that quantity is either positive or negative or 0. If it's positive, then the square root of a positive number is a positive number, and you'll wind up with negative b plus or minus a positive number over 2a. So you'll have like two real solutions. If this quantity is 0, well, you'll have b plus 0 and negative b minus 0. So there will only be one solution when that thing is 0. And if it's negative, well, you see two complex solutions. So with that reason, the discriminant of this polynomial is used to refer to the formula b squared minus 4ac. And how the nature of the roots of a degree 2 polynomial are determined by this formula, by this quantity. If the discriminant is bigger than 0, then, well, take a look. You're taking the square root of something positive, so you get a real number there. You have a real number plus or minus a real number all over 2 times a real number. So you wind up with two different solutions, which are real. If b squared minus 4ac is equal to 0, then there's only one solution. Right? Square root of 0 is 0, so this plus or minus doesn't matter, which is, well, also real. If b squared minus 4ac is negative, then there will still be two solutions, which are complex. Moreover, take a look at the two solutions. This will be the bit that has an imaginary thing going on. And so you have two numbers. You have negative b over 2a plus an imaginary thing, negative b over 2a minus an imaginary thing. Their imaginary parts are just strictly opposite. They're conjugates of each other. Cool. So I guess that's kind of handy. If someone hands you a degree 2 polynomial and you multiply together the two roots of that polynomial, you will always get a real number. Nice. So let's use this idea in some examples. Let's not actually find the examples. let's just answer, how many solutions do these things have, and what types are they? And maybe just for mindar's sake, the discriminant is b squared minus 4ac. So let's work it out, I don't know, in this example. So this equation has discriminant equal to b squared minus 4 times a times c. So that's 16, because that negative, right, it gets canceled with itself. Negative squared becomes positive. Minus 4 times 3 is 12 times 2 is 24. And you could work out what that is, but I don't care. It's less than 0. I don't care that it's negative 8. Negative 6? Well, the point is I don't care. Is less than 0. So look back at that previous page. Tell me about the solutions of this. I think it says that there are 2 complex solutions. And they're complex conjugates of each other. 3x squared minus 4x plus 12. Oh, that's the same thing again. That's not very useful. How about that? 3x squared minus 4x minus 2. So let's compute the discriminant. The discriminant is b squared minus 4 squared minus 4 times a times c. And now let's work out what this is. So just as before, negative 4 squared is 16. Double negative becomes positive. Plus 24. I don't know, I think that's 40, but I don't care that it's 40. All I care about is that it's positive. So I conclude there are 2 real solutions. 2 more. Let's just finish off this page. And I'm totally on time. Right, it's only 27 minutes in. Let's find the solutions to x squared minus 4x plus 4. Nope, not find the solutions. Let's just say how many there are. So the discriminant is b squared minus 4 times a times c. Oh, hey, that's 16 minus 16. Discriminant is equal to 0, so there is only one solution, and it is real. And just, well, I don't know, one last one. The discriminant of this is b squared minus 4 times a times c is bigger than 0, so I see 2 real solutions. Cool. People feel pretty okay about this? Hopefully it wasn't anything terribly deep. I get the intent is the stuff about the discriminant is the only stuff that's supposed to be truly new. Maybe you don't remember how to divide complex numbers, but now you know. Nice. So, I might see you Friday. We will see. Either way, talk to you in the future. Ciao.